Hi, welcome to our first press conference of the day, Wednesday, on the weak solar cycle and its consequences. We have Nat Gopalswamy, an astrophysicist with the Solar Physics Lab at NASA Goddard Space Flight Center in Greenbelt, Maryland. Joe Giacalone, professor and associate director of the Lunar and Planetary Laboratory at the University of Arizona in Tucson. Marty Mlynczak, sorry about that, senior research scientist with the Climate Science Branch at NASA Langley Research Center in Hampton, Virginia. And Leif Svalgaard, senior research scientist at the Hansen Experimental Physics Laboratory at Stanford University. Okay, thanks.
Okay, good morning. I'm going to briefly discuss about the solar cycle 24 and its consequences to the heliosphere. We all know that the sun is in its maximum phase, but the maximum phase is weak. As you can see from the sunspot number, this is cycle 23 and cycle 24. The sunspot number has significantly declined. And the reason people think is because the polar field in the previous cycle was smaller, and the polar field is supposed to feed the sunspots coming in the next cycle. This can also be seen in microwave emission from sunspot regions that is also declined. And we are in the maximum phase with the North Pole already finished its maximum phase and the South Pole in the midst. So what is the consequence of this weak cycle? The best way to look at is to look at the strength of geomagnetic storms that happened since 1957. For example, there are many solar cycles here from cycle 19 to cycle 24. And in cycle 24, the number of major geomagnetic storms measured by the index known as DST is the number is very small. And also the strength of the storm is also relatively small. For example, the March 1989 storm, which caused a big blackout in Quebec, is really huge. And the hollow wind storms here, and compared to those two, we almost have a very barely major storms. This is a plot of solar energetic particle events, or SEPs. And this is another source of space weather. And again, from cycle 24 to 24, the number of events, the big events, is again very small. Only 3 of them more than 1,000 units. So you have a weaker geomagnetic storms and weaker energetic particles events. Why is this? You know, these two space weather events, namely geomagnetic storms and energetic particles, are caused by coronal mass ejections, or CMEs. The CME rate itself is not very small in the cycle. You can see the rate is between 3 and 4 during the maximum phase, which is similar to the last cycle. So what's happening? One of the clues to the behavior of cycle 24 came from the fact that all the energetic particle events of cycle 24 were associated with halo CMEs. You know, halo CMEs are those which appear to surround the sun because they expand very fast early on. So that means there is something to do with the width of the coronal mass ejections, that is the size we see in the sky. So we looked at the width of the CMEs from cycle 23 and cycle 24, and we found that the cycle 24 CMEs are bigger for a given speed, as you can see from this. So if you look at 1,000 kilometers per second CMEs, these are the ones which cause the space weather events. You see that the cycle 24 events, the size is bigger by about 38%. So that means the CMEs are expanding more than usual. So why is the CMEs expanding more than usual? When we measured the pressure in the heliosphere, using satellites such as ACE and WIND, we found that the pressure is reduced in this cycle by about 40% compared to the previous cycle. Of course, we cannot directly measure the pressure near the sun, but we can extrapolate what we measure at 1 AU to near the sun, and we find that there is a similar reduction in pressure near the sun. So when CMEs are ejected into this milder, low-pressure heliosphere, then they puff up. When the CMEs expand more, the magnetic field inside the CMEs has lower strength. So when you have a lower strength magnetic field, then they cause milder geomagnetic storms. And the lower magnetic field in the heliosphere also contributes to lower efficiency of particle acceleration in the heliosphere. That's why we have no big energetic particle events, although the number of energetic particle events itself is not decreased significantly. So we have other panelists going to talk about the energetic particles and also what are the weak signals of the sun we see near Earth, in the Earth's atmosphere. Thank you.
Okay. My presentation follows on basically right on the heels of what Nat was saying right at the very end. I'm a theorist primarily, and so my talk yesterday in this session was devoted to trying to understand what it is about this weak solar cycle that it can tell us about how particles are accelerated at these shock waves, maybe to explain why we don't have the very large events. And quite frankly, Nat summarized it very nicely in just a couple of sentences at the end of his talk. But I'd like to illustrate this with a few slides as well. The important clues that we know for sure, one is that we know that these large SEP events are created by shock waves driven by coronal mass ejections. That's pretty well established, and I don't think there's a lot of argument on that point. There's not noticeably a fewer number of CMEs, and in fact, depending on how you count them, there could be more. I was hearing talks in yesterday's session that there's actually more CMEs. It's difficult to count the number of CMEs, but it's not obviously fewer, and in fact, quite probably more. The CMEs, are they faster? Again, it depends on how you count them. Some seem to be a little faster, but again, there's no obvious trend in that regard. One thing for sure, though, is that the interplanetary magnetic field, as Nat was pointing out, is weaker. That's known. That's been reported. There's been some news items. The ACE, Advanced Composition Explorer spacecraft, has a news item out that has a report on this. The interplanetary magnetic field is definitely weaker, and we know that. The solar wind flux is also weaker, and so these are things that we know. So how does this affect particle acceleration? Okay, being a theorist, Okay, so I tried to put this down into a slide, and I'm sorry, I don't have a chalkboard. Being a professor, I like to have a chalkboard and do this on the chalkboard, and so my slides are not professional quality. These are the ones that I could do the best I could to illustrate my point. The figure on the left is a standard cartoon illustration of a CME in the gray shaded region. That's a coronal mass ejection, which is a giant magnetic flux rope with entrained plasma that comes from the sun. The line out in front of it that's arced is a shock wave driven by that CME. And then the other curved lines with all sorts of little wiggles that sort of look like they're rotating around into space, that is called the interplanetary magnetic field, which is a Parker spiral magnetic field. And the particles are accelerated at the shock. Those little dots are particles accelerated by the shock. So if I blow up the little region there close to the shock, that's that little yellow figure with the blue lines, that's what's going on. Particles are going back and forth across this shock being accelerated. Okay, and this is a well-known mechanism. It was discovered in the late 1970s called diffusive shock acceleration. Okay, so that's the standard picture, but in the current solar cycle, and I'm sorry, all I did was expand that to make the point that when the magnetic field is weaker, the particles are not trapped near the shock as effectively. And there are equations that describe this, and that was in my talk yesterday, but basically in its simplest form, the particles are just not as effectively trapped. They're going much farther upstream and downstream of the shock wave, and it takes a lot longer for them to get to very high energies. So the upshot is if I'm plotting a spectrum, the flux of particles versus energy, the lower energy part is not going to be affected too much because that's just depending on what your source is. The solar wind is a little bit less, and so the vertical axis, it might be up or go down a little bit. But by and large, the biggest effect is that the weaker magnetic field leads to a lower energy cutoff. And so the largest events are the ones at the high energy end. And so you're just not having as many because you can't effectively trap these particles. So that's my main point. Now I wanted to take my last 50 seconds and make one additional point. Now I'm switching to galactic cosmic rays. The top panel is neutron monitor galactic cosmic rays. Okay, it's a proxy for galactic cosmic rays. During the last solar minimum, as I think most people are aware, the galactic cosmic rays reached an all-time record high. That's in that little pink circle up at the top, the largest on the top axis. And sunspot number is in the bottom. And the galactic cosmic rays actually they've been reduced during the solar maximum. When the sun is more active, galactic cosmic rays can't come in as effectively, and so it is in fact reduced. But you can see it's not nearly as reduced as previous maxima. So the galactic cosmic rays have gone down, yes, but not as far as in the past. And the only reason I want to bring this up, and I want to show this as my last slide as I'm running out of time here, my colleague Dick Maywalt, who's in the audience, has he has converted the neutron monitor galactic cosmic ray counts in that top panel to a dose equivalent felt by an astronaut behind a certain amount of shielding. And that's what this plot is. So you can see the cosmic rays in the red there, but it's now, the axis is not cosmic ray counts, but it is dose equivalent instead. And I've put on the right that the top of that axis is roughly equivalent to 10,000 chest X-rays. And the number in the middle is about 1,000 chest X-rays. This would be the dose equivalent felt by an astronaut on a 6-month mission behind a certain amount of shielding, as seen in this slide. And you can see that during solar minimum, when the galactic cosmic rays are the highest, the field is the weakest, you're at about the yearly limit for NASA astronauts that they pose. So it's a difficult problem to send people to Mars, for example. But the point I wanted to make, and this does not go all the way to the present, but if you combine that with this picture right here, the galactic cosmic rays have come down, but not that far. So in other words, it is, if I were to plot this in 2014, it goes up, but not nearly as much as those peaks in that plot. So maybe if you want to go to Mars, maybe now would be the time. Okay, galactic cosmic rays are lower, but not. Excuse me, galactic cosmic. The dose equivalent is high, but not as high as previous times, and the number of SEPs, which are the other problem, are down. So this might be the time to go. So, okay.
Okay, I'm Marty Mlynczak from NASA Langley, and Linda Hunt and Jim Russell, who are in the room, have also contributed to this presentation. We're going to take a little bit of a different tack right now. We're going to look at the consequences of the current solar cycle from the perspective of the upper atmosphere and how the sun is, as I'll say on the next slide, imprinting its natural variability up on the Earth's highest atmosphere. So I'm going to identify the atmospheric region of interest, so we all know we're talking about the thermosphere and not the troposphere down here where we live. I'll talk a little bit about basic ideas of energy flow in the upper atmosphere, very simple concept behind that. Then we're going to look at data from 2 NASA instruments which are currently in orbit on the NASA TIME satellite, the SABRE instrument and the SEE instrument. The SEE measures the input from the sun, SABRE measures the infrared radiation from the atmosphere back to space that cools the atmosphere. The key results I want to talk about are, again, this imprinting of the natural variability of the sun on the thermosphere, on the atmosphere, and that we have 12 years of data to really observe this for the first time in detail. And then at the end, I'll tell you why this is important and why we're concerned about this, other than just a basic science curiosity perspective. So in this slide, we have the typical view of the atmosphere and the various layers: troposphere, stratosphere, mesosphere, and thermosphere defined, in a sense, by the sense of the temperature gradient in each layer. The focus of the talk today is above 100 kilometers, between 100 and about 250 kilometers, where SABRE measures the infrared emission from the upper atmosphere and monitors that for the last 12 years. We're not talking about climate near the surface of the Earth. We're talking about 100 kilometers and up. So in very general terms, we have the sun inputting both ultraviolet light and the solar wind particles into the thermosphere. The net effect there usually is to heat the thermosphere, it warms up, and then, is there a pointer? I'll shoot over everybody's head here. We have carbon dioxide and nitric oxide. These are very active infrared molecules, infrared emitting molecules, and they act as, we call this, a natural thermostat to remove energy from the thermosphere and cool it down as the sun varies or as the sun varies and heats up in the atmosphere. The CO2 and NO remove that energy. And so we're going to look at the inputs and the outputs, basically, into this system. So here's 12 years of data from the NASA C instrument on the TIME satellite. And it shows a time series back from 2002 January up until almost the present day of the ultraviolet radiation from 0 to 200 nanometers entering the Earth's atmosphere. We've had about a 20% decrease in UV over that time. And so the question is, how does the infrared cooling respond as the UV decreases? And so SABRE measures, as I said, infrared emission from CO2 and nitric oxide. And what I have here is a time series. Each bar is a 2-month average. And we've taken the average here. We've removed the long-term mean. So you can see the effect of CO2 emission greater back here at solar maximum. It goes down during the long and deep solar minimum, and back up here at the current maximum, which you can tell by eye it's a lot weaker than the prior one in 2002. And it's actually weaker in the sense that over a year we've had 1 trillion kilowatt hours more energy emitted by CO2 in 2002 than we did in 2013. And nitric oxide does the same thing. If you add it up, you can see again the solar cycle there in nitric oxide. That's this imprinting of the solar variability on the upper atmosphere. And again, about 1 trillion kilowatt hours of energy more emitted by nitric oxide back in 2002 than in 2013. So to give you just a summary of what this all means, the current solar maximum conditions are substantially weaker to the tune of about, over a year, 2 trillion kilowatt hours of energy more back in 2002 than in 2013. And that's about 10% of the U.S. annual energy production. It's a lot of energy up in the upper atmosphere. And again, I've made this point that the solar variability imprints substantial natural variability on the upper atmosphere, on the Earth's thermosphere. So the question is, why does this matter beyond scientific curiosity? And the reason is that CO2 is increasing in the atmosphere, not just down here where we live, but all throughout the atmosphere. And it's predicted to cool the thermosphere substantially in coming decades. And I put here the top from a paper by Ray Roble, who got the AGU Bowie Medal last night, and Bob Dickinson from 1989, in which this was first explored and put out, the idea of cooling of the upper atmosphere due to increasing CO2, methane, and so forth. And so this is a fundamental prediction. And the point is that if we want to detect the cooling trend in the upper atmosphere, we've got to understand the variable sun and how it modulates the thermosphere in a natural way. And that's the key point here, is we have to understand this natural variability, and then we can understand the trend. One consequence, a very critical consequence for space operations, is as the thermosphere cools, it has less density at a given altitude, and you get longer lifetime for satellites, which is great, but space junk also lasts a lot longer. And so for operational considerations, there's a lot of concern over this, just so we can continue to track space junk and deal with it for satellite and space station operations and so forth. And finally, then, we have the C and SABRE records are really the necessary first steps in understanding this natural variability that we need to assess trends. And for further information, Linda Hunt here has a poster on Friday in the session there that you're welcome to come by and talk more about this. And thanks.
Okay, I'm Leif Svalgaard from Stanford University, and I'm going to talk a little bit about the past cycles and maybe the future cycles. This cycle is a weak one, and actually it was predicted. What I show on this slide, what happened? Here it is. If I can get it to show. The key thing we use to predict the sunspot cycle with is the polar fields of the sun. So here's kind of a schematic image of the sun, and the polar fields we measure in this little square here and down there. And the theory is that the polar fields are dragged into the sun, magnified in here, and reappear as sunspots. And this cycle just goes on and on. And here are the last 4 cycles of our measurements. You can see that the polar fields have gone down, and the sunspot number down here has also gone down. And that's the basis for the very simple prediction we have, namely that lower polar fields mean lower sunspots, and therefore lower solar energetic particles, lower magnetic storms, and so on. This was, a few years ago, this was controversial. People were predicting a very large cycle, but I think now that the sun has shown us that the polar field prediction method actually works. So based on this, if we can measure the polar fields for the next cycle, then we can probably predict it. Now, we can't measure that right now because the polar fields have disappeared. You can see here they have decreased to nothing. Can't even point. But in 2 or 3 years, the polar fields will have built up again, and by observing at that time, we can probably predict what cycle 25 is going to be. So how is that prediction of 24 going? Well, you can see it here. I can't get this into one. There we go. So here's the last 3 cycles or so. The dashed line here is the predicted curve, and you can see the sun is following very nicely. Here's another view of that due to David Hathaway. And way back 100 years ago was something called solar cycle 14. And cycle 24 is beginning to look very much like solar cycle 14. That is 14 is behind here, and this new one coming up is 24. And here's the last 300-400 years of sunspots, and there's cycle 24. It's the lowest in 100 years. Here's cycle 14. And 100 years before that, they were down here, and 100 years before that, they were here. So, although this is a weak cycle, the sun has been there before. This is not something new. It is new for us. It's not new for the sun. Now, there's an interesting issue here, and that is solar activity now is back to where it was 100 years ago. So we would predict that the consequences of that now would have been like the consequences back then. For example, you can talk about the climate. Is that any different or not? If the sun has anything to do with that, we would expect cycle 14 and cycle 24 to kind of give us the same kind of climate. None of that, we don't really know how that works. But having solar cycles of different sizes gives us a baseline or a way of, or a measure of the variability, and from that we can probably learn something about what will happen in the future. So for me as a solar physicist, cycle 24 is extremely exciting. It's a chance to learn something new. The previous cycles that I have lived through were more or less the same. When nothing changes, you don't learn anything. When things go out of whack and become strange, that's when you learn. So we look forward to cycle 24 evolving, and even more to cycle 25 to come. We'll see what consequences we get out of that. Space weather might be slightly milder, but judging from the past, we think that the extreme events that are a danger to our infrastructure and to astronauts and so on will probably not be more rare. They're rare to begin with, and they can occur at any time, low solar activity or high solar activity. So that's a dark horse. We don't know how that will go. But that's what what cycle 24 is doing. And let's see about the consequences. That's a fascinating thing to watch. None of us alive have ever seen such a weak cycle. So we will learn something. Thank you.
Are there any questions?
Harvey Lyford, freelance. It's a very fundamental question. What exactly do you mean by polar field? And what is a weak one and what is a strong one?
Well, the polar fields are the sun's magnetic field measured at the poles. And that we can measure by studying the light that we get from the polar area. And we have at the Wilcox Solar Observatory near Stanford, we have kept track of that for the past 30, 40 years. And we measure it every day. In theory, our current theory predicts, or assumes maybe rather is a better word, that field which we measure at the surface near the pole is advected or is moved back into the sun, moves down towards the equator, and while it's down there, it's being magnified by something called the solar dynamo. And a strong magnetic field at depth is buoyant. It's like putting a cork in water. It will pop to the surface, and sunspots do that, and that's how we close the cycle between the polar fields and the sunspots. So the polar fields are important for understanding how many sunspots we will get, because obviously the more polar field we have, the more spots we can probably get. And this can all be put into fancy mathematical models and so on, and it all checks out nicely.
Hi, Kate Green, freelance. Can you tell me a little bit more about the solar cycle that was at a minimum 100 years ago, and what solar science was like, how we know that, and what the consequences were 100 years ago?
Yes, of course, 100 years ago we did not have any satellites. So all the effects on space we were not aware of. People were measuring only the sunspots, and of course, that's how they counted low number of sunspots. So low solar activity also means the sun can actually cool a little bit Earth's surface, right? And probably that's very well felt during the Maunder minimum that happened, in the late 1600s. But 100 years ago, I'm not an expert on that, what happened, so.
Well, maybe I can say a little bit about that. Although we didn't have satellites, we did have some technological infrastructure that were influenced, like telegraph lines, for example. And even before cycle 14, back in 1859, was something called the Carrington event, a big flare and CME on the sun. And that one actually was interfering with telegraph communication. You could actually switch off the current to your telegraph system, and the induced current from the sun would be enough. Sometimes it went even beyond that. Telegraph stations would catch fire. People would get electrical shock when they were trying to send a message. And there have been others like that. One, for example, in May of 1921, was a similar one. I believe personally it was as large as the Carrington event. They're still being debated a little bit. There was of course, these effects are largest up at higher latitudes, where you have the biggest effect of the solar storms. And a little town up in Sweden had just installed a new telephone exchange. And everybody had cables going out to their telephones and so on, big news. And they even had an automatic fire alarm. There were in each street corner, there was a little thing you could push if there was a fire, and it was connected with the telephone lines and to the fire station and so on. Unfortunately, due to this storm, the telephone exchange caught fire and burned down. And so you couldn't even alarm the fire department, because those alarm systems were depending on the telephone system working, and it didn't. There's a little anecdote there. The thing was, the exchange was insured for 200,000 Swedish crowns, but on April 1st, just before the storm, the insurance policy lapsed because people thought, well, it's too expensive. So there you have it, right? So those technological effects, if you like, of solar storms are very real, and they have happened in the past, and they will happen again.
If I could just add, one thing that was not mentioned was also auroral activity is also another thing that was known to be, you could see aurora very far at southerly latitudes during very large storms. That was pretty well documented.
So I think we have two questions from the chat.
Okay, the first question is from Seth Borenstein. It's a question for Dr. Mlynczak. How does this translate to near surface temperatures on Earth? What kind of forcing chance do we see at the surface from the sun now compared to more normal max, and how does that compare to anthropogenic forcings?
Okay, I think there's several questions there. I'll try to answer what I think I heard. The effects of this right now and what we're showing in the thermosphere really have no known effects on the troposphere. The amount of energy, even though it's a lot, when you average it over the globe, it's really milliwatts per square meter, whereas the climate system down where we live here is driven by hundreds of watts per square meter, so there's really no impact that we know of or any way to amplify that energy coming in to have it make any type of an effect on Earth's surface or Earth's climate. It really is an issue for the upper atmosphere alone. Was there another question? I think I kind of caught everything on that with that answer. I hope I got it.
Yeah. Okay, so the second question, this is a question from Monica Young, who's reporting for Sky and Telescope. This is a question for Dr. Svalgaard. Aside from waiting another 100 years, is there any way to test whether and why there is a 100-year cycle for solar activity?
And that's a very good question. There's no doubt that there is one. You can see it by eye here. Why there is one? The honest answer is we don't know. The sun is a complicated mechanism. The Earth's climate is complicated too, and any complicated system has internal oscillations, internal variations, and it may be just what we normally call stochastic. So I personally do not believe there is a strict 100-year cycle. We cannot extend this one back in time indefinitely, and we cannot expand it into the future indefinitely. Definitely. So this 100-year cycle has been observed a few times, but I don't think it's an inherent, strong, strict cycle in the sun.
So we had some technical difficulties. So
Yeah, so the question I first asked to Dr. Mlynczak, because of a failure of our web stream, the reporter who asked it wasn't able to hear your answer. So
Okay.
shall I read it again?
Sure, go ahead. You would,
Okay.
please.
The question was, how does this translate to near surface temperatures on Earth? What kind of forcing chance do we see at the surface from the sun now compared to more normal max, and how does that compare to anthropogenic forcings?
Okay, and I'll try to give the same answer I gave him before. The impacts that we're talking about here today are really confined to the thermosphere. There's no known impact at these wavelengths and so forth on the Earth's surface, on surface temperature. The amount of energy that we're seeing, these differences that we're talking about are milliwatts per square meter, whereas the climate system that down at the Earth's surface here is driven by hundreds of watts per square meter. So we don't know any effects from the on climate from this right now. What you really have to look at, which I haven't, is how the total solar radiance is varying, and I think it's been varying quite small, and that there really is not a climatic effect here on our surface.
any other questions? Oh, it's just for reporters. Are you? Yeah, sorry. Any other
see if
questions
there's
in the
any-
chat?
let me see if there's any from the chat. No.
No. Okay, thank you.
Okay,
Thank
thank
you.
you.